Actually, we are discussing about one of the important topic from the organic chemistry, heterocyclic compounds. In last lecture, we have studied first heterocyclic compound in detail, pyrrole. Pyrrole is actually five-membered nitrogen-containing heterocycle. Now let us see next heterocyclic compound, and this is nothing but the pyridine molecule. What is meant by pyridine? And here also we are going to discuss in detail about that pyridine. Similar to pyrrole, we have to study in detail about the pyridine. Now let us see first what is the structure of pyridine. Yes, it is very simple compound, just like benzene. It is six-membered compound. But instead of one carbon, there is one nitrogen atom. Okay, and it is six-membered nitrogen heterocycle. This is six-membered nitrogen heterocycle. Similar to the benzene, it is also aromatic in nature. Why it is aromatic in nature? Because there are three pi bond. Means there is six pi electron. Means there is a Fourier plus two pi electron. And it obeys Huckel's rule, and therefore pyridine is aromatic in nature, and thus pyridine is a six-membered aromatic heterocycle having one nitrogen atom. It is also known as azine, and generally it is found in the bone oil as well as fractions of the coal tar. Okay, and thus this is just about the introduction of pyridine. Very important example of heterocyclic compound. Actually, it is six-membered. It is aromatic in nature and also called as the azine. Now let us see synthesis of pyridine. Synthesis means we are going to discuss how that compound is synthesized in laboratory. First, very simple method by using acetylene. Acetylene means CH triple bond CH, a best example of alkyne. Okay, this is CH triple bond CH acetylene. Now, in this reaction, in this synthetic method, when that acetylene is treated with the another compound, hydrogen cyanide HCl, two molecules of acetylene participate in the reaction, and when that acetylene and hydrogen cyanide is passed through a red hot tube, the mixture of acetylene and hydrogen cyanide is passed through red hot tube. Here two molecules of acetylene and one molecule of hydrogen cyanide participate in the reaction. Now let us see how the reaction occurs. Actually, that molecules undergo cyclization. Here, one pi bond undergo breaking and new bond between carbon and nitrogen is formed. Simultaneously, this bond, pi bond undergo breaking and new bond between that two carbon is formed. Simultaneously, one of the pi bond undergo breaking, and here there is formation of new bond, and thus we get the cyclic compound. Now there is a double bond between carbon and nitrogen. Here this is new bond, here this is new bond, and here this is new bond, and we get the six-membered cyclic compound having one nitrogen atom, and this is nothing but pyridine. And thus we can synthesize, we can prepare pyridine by using hydrogen cyanide and acetylene. When that mixture is passed through the red hot tube, we get the pyridine. Okay, this is very simple preparation method, very simple synthetic method. Now let us see in second method, it is prepared by using Piperidine. First, tell the name of this particular compound. What is the name of this particular compound? How many carbons are there? 1, 2, 3, 4, and 5. Thus total there are 5 carbon atoms, and it also having 2 amino group. Hence name of this compound is this is pentamethylene diamine. Now suppose that pentamethylene diamine is created with HCl. What should be the product? We know that it is example of base. NH2 group means it is base. When it is created with the acid, when it is created with the HCl, there is the formation of salt. We get corresponding salt, and this is nothing but the pentamethylene diamine hydrochloride. Okay, this is our starting material, pentamethylene diamine hydrochloride. When this compound is heated, when it is strongly heated, now what happens here? This molecule loses one HCl and one molecule of NH4Cl and undergoes cyclization, and we get the cyclic compound, and that six-membered cyclic compound is called Piperidine. And thus in first step we have synthesized the Piperidine. Okay, pentamethylene diamine hydrochloride, when strongly heated, undergoes cyclization. There is a loss of one HCl molecule, one ammonium chloride molecule, and we get the cyclic compound called Piperidine. Now this Piperidine further on reaction with palladium. This is a well-known catalyst used for the dehydrogenation. Palladium causes dehydrogenation. Dehydrogenation means loss of hydrogen atom. Now, how the reaction occurs? Here, from each of the atom of pyridine, there is a loss of one hydrogen. Means total there are 6 hydrogen atoms. They are removed, and thus we can say that there is a loss of thrice H2 molecule, and we get the cyclic compound having 3 pi bond, one nitrogen atom. It is 6-membered compound, and this is nothing but our pyridine. That compound is our pyridine, and thus we can synthesize pyridine from Piperidine. First, pentamethylene diamine hydrochloride, if allowed to heat strongly, it undergo cyclization, we get Piperidine, and it on further dehydrogenation with palladium, loses 6 hydrogen atom, loses 3 hydrogen molecule, and there is the formation of cyclic compound, and that cyclic compound is a completely aromatic, having 3 pi bond, and there is 1 nitrogen atom, and this is nothing but our pyridine. Okay, this is just a synthetic method used for the preparation of pyridine. Now let us see next point, very important point, resonance effect, how the pyridine undergoes resonance. What is the resonance? Yes, there is a delocalization of pi electron in conjugated system. Let us see how the pyridine undergoes resonance effect. This is the structure of pyridine. It having 3 pi bonds. There is just a delocalization of this 3 pi bond occurs. Means here this pi bond shifted in between these 2 atoms. Similarly, next pi bond is shifted here. Then again next pi bond is shifted here, and we get the first resonating or canonical structure of the pyridine. Now again there is a delocalization. Nitrogen is more electronegative. Hence, that pi bonded electron pair goes towards nitrogen and acquires negative charge on the nitrogen, while that carbon now acquires positive charge. And we get one more resonating structure for the pyridine. Now, what is the next possibility? Here there is pi bond. While this carbon having positive charge, means it is electron deficient carbon. Therefore, this pi bonded electron pair, this pi bond is shifted here. Pi bond is shifted also. Hence, that next carbon acquire positive charge. Okay, this is the new position of pi bond. While this carbon now acquire positive charge, we get another canonical structure. This is the new canonical structure. Similarly, again, what is the possibility for the delocalization? Here, this is pi bond, and it is shifted towards that electron deficient carbon. Pi bond ikde shift hoto, it is shifted towards electron deficient carbon. Therefore, now next carbon acquire positive charge. Okay, now this carbon acquire positive charge, and we get one more resonating structure for the pyridine. And thus, in pyridine, there is a delocalization of pi electron, and due to this delocalization, we get number of canonical structure. We have studied how there is a delocalization of pi electron, how we get number of resonating structure. Now let us see some conclusion for that resonating structure. Now what should be our conclusion from the resonating structure? Here, the positions 2, 4, and 6 carries a positive charge. There is a positive charge on that carbon. Hence, it undergoes nucleophilic substitution reaction. Pyridine undergoes nucleophilic substitution at position 2, 4, and 6. Actually, pyridine is example of aromatic compound. Generally, aromatic compound undergoes electrophilic substitution, but unlike to the other aromatic compound, that compound undergoes nucleophilic substitution. And at what position nucleophile attack? It attack at the position 2, 4, and 6. Why the nucleophile attack at that position? Because that position are electron deficient. There is a positive charge on that position, and we know that our nucleophile is negatively charged. Nucleophile is always negatively charged. Hence, that nucleophile position 2, 4, and 6. Okay, this is the first conclusion, how actually pyridine undergoes nucleophilic substitution at position 2, 4, and 6. Okay, now let us see one more conclusion. What's about the remaining position? Remaining means that 2 positions, 3 and 5. That position 3 and 5. What's about the 3 and 5? That position do not having positive charge. Therefore, comparatively, that positions are electron rich. That positions are electron rich, and hence electrophile can be easily attacked on the pyrrole at position 3 and 5. Hence, that compound pyridine undergoes electrophilic substitution at position 3 and 5, while it undergoes nucleophilic substitution at position 2, 4, and 6. This is just about the two important conclusions from the resonating structures of pyridine, how it undergoes electrophilic as well as nucleophilic substitution, and at what position that substitution occurs. Okay, this is just about the resonance effect shown by pyrrole. Now, let us see, yes, important concept about the basic nature of pyridine. About the basic, yes, that pyridine having nitrogen. Now, why the nitrogen containing compounds are basic? Amines are basic in nature due to presence of lone pair of electron under nitrogen. Suppose example RNH2 primary amine, that nitrogen having lone pair of electron, that compound can donate this electron pair to another substance, and hence it is basic in nature. Okay, generally amines are basic because they can donate this electron pair to another and act as a Lewis base. Now, what's about the pyridine? Yes, this is the structure of pyridine. Nitrogen having lone pair of electron. There is a lone pair of electron under nitrogen. And now this compound can donate this electron pair. That pyridine can donate this electron pair to another substance. And hence it acts as a basic in nature. That nitrogen can donate this electron pair to H plus ion and form a bond with hydrogen. Nitrogen acquires positive charge, Cl acquires negative charge, and thus during that process, the nitrogen atom of the pyridine donate electron pair, it undergoes protonation, and therefore it acts as a base. Therefore, it is basic in nature. Okay, this is just about the basic character of the pyridine, why it is basic in nature. This is very interesting concept. Comparison of basic nature of pyridine and pyrrole. First, tell me why the amines are basic in nature. Pyridine as well as pyrrole, both are amines. Why they are basic in nature? Nitrogen having lone pair of electron, they can donate this electron pair to another substance, and hence they act as a Lewis base. This is very common statement. Okay, let us see example of pyrrole. In pyrrole, nitrogen having lone pair of electron, and we know that this electron pair is involved in the delocalization. We have studied how the lone pair of electron on the pyrrole is involved in the delocalization. We get number of resonating structure, and we can simply say that this electron pair is involved in delocalization and aromatic sextate, and therefore this electron pair is not easily available for donation to another compound. This is not easily available for donation to another compound. Hence, it is weak base. Why it is weak base? Because this electron pair is involved in the delocalization. It is involved in the aromatic sextate, and it is not easily available for donation to another compound. Hence, it is weak base. Now, what's about the pyridine? In pyridine, there is also lone pair of electron, but in pyridine, already it having 3 pi bond. 3 pi bond means there are 6 pi electrons. Already pyridine having 6 pi electron. Therefore, this lone pair of electron on the pyridine is not involved in the delocalization. What is my statement? The lone pair of electron from the nitrogen is not involved in the delocalization in pyridine. Therefore, that electron pair is easily available for donation to another compound. Hence, it is comparatively strong base. Hence, it is comparatively strong base, and thus pyridine is a more basic than pyrrole. Why it is more basic than pyrrole? Because pyrrole having a lone pair of electron, it is involved in the delocalization and aromatic sextate. Therefore, that electron pair is not easily available for donation. Hence, pyrrole is weak base. Now, what's about the pyridine? The lone pair of electron is not involved in the delocalization. Therefore, it is easily available for donation to another substance. Hence, it is more basic than pyrrole. Okay, this is just a comparison between the basic nature of pyrrole and pyridine. And let us see one more concept, comparison of basic nature of pyridine and aliphatic amine. This is example of alkyl amine or aliphatic amine. Yes, that aliphatic amine, our pyridine, both are amine. Why the amines are basic in nature? Because they contain lone pair of electron. They can donate this electron pair to another substance, hence act as a base. Now, what's about the aliphatic amine? In aliphatic amine, nitrogen having lone pair of electron. Okay, but that nitrogen is attached to the two alkyl group, means it is attached to the sp3 hybridized carbon. Both the carbons are sp3 hybridized. And if the carbons are sp3 hybridized, they show the plus I effect, means there is electron donating inductive effect. Means that bonded electron pair is just pushed towards nitrogen. This electron pair is also pushed towards nitrogen. This is called electron donating inductive effect. Due to plus I effect, electron density on the nitrogen increases. There is more electron density on the nitrogen. Hence, electrons are easily available for donation. And hence, that aliphatic amine is more basic. Let us see example of pyridine. Now, what's about the pyridine? In pyridine, nitrogen having lone pair of electron, but that nitrogen is attached to the carbon. Now, what is the nature of this carbon? Yes, this is double bonded carbon. This carbon is also double bonded. Double bonded means what is the hybridization of that carbon? Yes, hybridization is sp2. Means in pyridine, nitrogen is attached to the sp2 hybridized carbon. In nitrogen is attached to the sp2. Actually, this is sp2 hybridization. Here also that carbon is sp2 hybridized. And if carbon is sp2 hybridized, then what is the nature of inductive effect? There is a minus I effect. Means that bonded electron pair इथं मायनस आय इफेक्ट दाखवतो sp2 हायब्रिडाइज्ड कार्बन. म्हणजे नायट्रोजन आणि कार्बनच्या मध्ये जो बॉन्ड आहे, कोव्हलंट बॉन्ड आहे, दॅट इलेक्ट्रॉन पेअर इज अट्रॅक्टेड बाय sp2 हायब्रिडाइज्ड कार्बन. म्हणजे sp2 हायब्रिडाइज्ड कार्बन असल्यामुळं होतं काय, देर इज इलेक्ट्रॉन विड्रॉइंग इंडक्टिव्ह इफेक्ट, देर इज मायनस आय इफेक्ट, अँड देअरफॉर electron density on the nitrogen decreases. There is a decrease in electron density due to minus I effect. मग electron density जर decrease झाली nitrogen वरती, then the availability of lone pair of electron on the nitrogen for donation is decreases. म्हणजे hence electrons are not easily available for donation. Hence it is comparatively weak based than aliphatic amine. Okay, this is just about the basic nature of pyridine. बेसिक नेचर मध्ये आपण 3 पॉइंट स्टडी केला. कुठलं बघा, फर्स्ट हाऊ द pyridine is basic in nature, then second one is the comparison with pyrrole. Actually it is more basic than pyrrole, and then second one is the pyridine is a less basic than aliphatic amine. Okay, we have studied how it is less basic than aliphatic amine. Okay, this is just about the basic nature of pyridine.